Hello everyone, this is Dr. London, and I just want to finish up this week talking about 6.3 measures of dispersion. So some just kind of statistical concepts that tell us about how spread out our data is, whether it's clustered together, whether it's spread out, things like that, how far apart our values are, some ideas like that. So, well, let's talk about some of the basic ideas. So how far apart our data is. So we have a couple notions there. The most basic of which is range. So the range is a pretty elementary concept. The range is just your maximum data value minus your minimum data value. Another one that comes up that you'll occasionally run into, we won't do too much with, is also known as the mid-range. So the mid-range, what is that? The mid-range involves the range as well, but it's a little bit different. It's actually so some of these topics kind of overlap, so maybe this was better talked about as a measure of center, but this is an average of your max and min. So your mid-range is your max plus your min divided by 2. So you're just averaging your largest and smallest values. So let's look at an example. Just computing these. So example, let's go ahead and calculate the range and mid-range of the following data set. So let's say we have these numbers, and they won't be, I just took this example from the book, so the data is unordered. But really, we don't even need to order it. We just need to identify the smallest and largest values in order to compute the range and the mid-range. So our smallest value here is 16. This is our minimum, and our largest value here is 86. That's our maximum. So we know that our range is going to be 86 minus 16, which gives a value of 70. So the distance between our largest and smallest values is 70, and the mid-range, which is the average of those two quantities, is 86 plus 16 over 2, which is 51. So that's another way to kind of think about the middle. Again, last time we learned about the average. You could add all 5 numbers together, and then you could divide by 5. That would be the average or the mean. And then median, you could write them in increasing order and look for the middle number. So in this data set, that would be the third smallest or largest value, which would be 33. So the mid-range is quite a bit different from that. Okay, so why don't we talk about the kind of the most, I guess, kind of mathy thing that we have in terms of doing these things. So what do I mean? The most computationally intensive is talking about the standard deviation. And I will say there's kind of two notions of standard deviation, a population standard deviation and a sample standard deviation. For all of our data sets, we're just going to consider them samples. So when we talk about the standard deviation, it's going to be a little bit different. And they do talk about they use some series notation for the formula. I'm going to show you how to do it just using a table. So it's going to be a little bit different. And then we'll finish by looking at how the standard deviation applies to a really prevalent distribution in statistics called the normal distribution. So so we won't be writing down the specific formula, but kind of naively we could just kind of define it this way. We'll look at how to compute it from small data sets, and again go into it with the normal distribution a little bit when we get there. So what is this? This is basically the standard deviation. Sorry, I misspelled that. So the standard deviation is a statistical measure of dispersion that shows how data vary about the mean. So let's go ahead and look at how we would do this in an example. So example, so find the standard deviation of the following sample data set. So let's say our data set is as follows: 36, 71, 28, 51, and 31. So the first thing you want to do is find the average. So a lot of times when we're using some sample values, the average is represented by x with a bar on top of it, x bar. So in this case, again, we just total those numbers and then divide by 5. So 36 plus 71 plus 28 plus 51 plus 31, with everybody being divided by 5. So this average comes out to 43.4. So then what we want to do from there is we want to make a table. So what this table will do is it will kind of break down how to do this formula step by step. So in the first column, we're going to list x, all of our observations. And in the next column, we're going to do x minus the average, x bar, which is going to be the what's known as the deviation. And in the third column, we're going to do x minus x bar, and we're going to square that number. So we're going to take the number, subtract, so that we're going to write down our numbers in the first column. So 28, 31, 36, 51, and 71. And then in this next column, from each of those numbers, we subtract the average. So 28 minus 43.4 comes out to minus 15.4. 31 minus 43.4 is negative 12.4. 36 minus 43.4 is negative 7.4. 51 minus 43.4 is 7.6. And 71 minus 43.4 is 27.6. So the reason that we have to square all of these deviations is you might think to yourself, well, maybe a good way to measure the average dispersion is to just take the average of all of these deviations, the second column. Well, it turns out you can't do that, because if you look at the total of all these deviations, that is, if you add up all these numbers in the second column, they will always total to 0. So you don't get any information that way, because all the numbers below the mean, their distance plus all the numbers above the mean, those are always going to add up to 0. The total distance away from the mean is 0. So if we square them, we get a bunch of positive numbers, and then basically what we can do is kind of take kind of an average and then a geometric, and basically what we're going to do is we're going to divide by the degrees of freedom, which is the number of data points minus 1, and then take the square root of that value. So in this third column, that's all we're doing is we're squaring the number. So negative 15.4 squared is 237.16. 12.4 squared is 153.76. 7.4 squared is 54.76. 7.6 squared is 57.76. 27.6 squared is 761.76. So this is the column that we want to total. So if you add those 5 numbers in the third column together, you get 1265.2. So that's the total of that column. So then the last thing we do to figure out our standard deviation, so our standard deviation, which a lot of times with this, for sample sets, we will denote the sample standard deviation with just an S. What we do is we just take that 1265.2 and we divide by 1 less than the total number of data values we have. So we have 5 data values here, 28, 31, 36, 51, and 71. So what we want to do is we want to take this number that we just got, 1265.2, divide by 5 minus 1, which is 4, and then take the square root of that. So that value comes out to about 17.78. And that is how we find the standard deviation by hand. So it seems a little complicated, but it's something that comes up. If you ever take the GRE, at least I don't know if this is still on the syllabus for that standardized test, but it does happen to come up there. But if you want to check to make sure that you're getting this right on your homework, I'll show you how to find it on Excel as well. So let's say we open Excel, we can type in those 5 numbers, and so let's again make this a little bit bigger so you can see. So let's type in our data values, 28, 31, 36, 51, and 71. Okay, so what we do is we type equals if you want to do a formula, and then standard deviation. So we see 2 options here, standard deviation .p and standard deviation .s. So if you know the difference between a population and a sample, that tells you which one to choose. For all of our computations on the homework, we're using standard deviation sample. The difference basically is if it's a population, you divide by n, the number of data points, and if it's a sample, you divide by n minus 1. So let's do standard deviation .s. And we want to select our data and hit enter, and notice you get the same number that we got. So that's another way to get the standard deviation if you want to check your answers on Excel. But you can do it by hand, you can do it by Excel, and obviously it's going to be much quicker if you do it on Excel, but it's always nice to make sure you can do it by hand and then get the correct answer that way. All right, so that is computing the standard deviation. So let's talk a little bit about the normal distribution. This isn't on my math lab, but it's possible that we might have another assignment on it. So if you take a class in statistics only, then you will talk a lot about the normal distribution. So let's go ahead and talk about that. So the normal curve, or the Gaussian distribution, it's sometimes called. So the normal curve, sorry, I hit a button there by mistake. Again, still kind of getting used to writing on this tablet. So the normal distribution, we're not going to get into any specifics with the formula. The normal distribution is a unimodal, meaning it only has one peak, symmetric, and bell-shaped curve. It arises in all sorts of applications in nature and different data values and things like that, but basically it looks something like this. Another thing, if you would look at the area below this thing, that whole area, area is equal to 1. And because the area is equal to 1, we use the normal distribution to determine the probabilities of certain events. So when you have a curve where the area below it is equal to 1, you can think of the area of subintervals as probabilities, because 1 would be 100%, so subintervals would be certain percentages, parts of the whole there. So that's one of the reasons it's important for the area below that normal curve to be equal to 1. So there's lots of different computational tools that will allow us to find those formulas given two parameters for the normal distribution in order to be able to determine the probabilities that you're looking at for these events. You need to know the mean of the distribution and the standard deviation. So these are tied to the standard deviation, and we'll see how that's done for all of our problems. If they come up, we're going to be given the mean and the standard deviation, and we'll go from there. We're not going to get into anything more complicated than that. There are a lot of computational tools and tables that will show you very, very precise areas and percentages, but we're just going to look at what's known as the empirical rule, which gives us basically probabilities for percentages that arise frequently in practice. So the empirical rule as it's known, or also the 68, 95, 99.7 rule, because those are the probabilities that arise, says what? It says, given data that behaves according to the normal distribution, one 68% of data is within one standard deviation of the mean. Two 95% of data is within 2 standard deviations of the mean. And 3, if you go 3 standard deviations on both sides of the mean, you contain 99% of all observations. So probabilistically now we've identified how much of the data is a certain distance from the mean. So basically we have some type of picture. You kind of have your normal distribution that you can draw like this, and then your mean is just this value that goes right through the center peak. This would be your mean, and then whatever your standard deviation is, you would count by that. So you have 1, 2, 3 lines on this side, and then you have 1, 2, 3 tick marks on this side, and basically between the first tick mark on either side, we've got 68%, and then if you would go from the second one over to here, we've got 95%, and then if you look from here to here, you've got almost everything, 99.7% of all observations. Now we can use some symmetry arguments to figure out more probabilities than just 68, 95, and 99.7. And we'll see how to do that through some examples. So let's go ahead and look at our first example. So one of the places where IQs often pop up is IQ tests, or at least scores on IQ tests. So and IQ test has a mean of 100 and a standard deviation of 15. I think these are typically the parameters on the Stanford Binet IQ test. What percentage of individuals have an IQ between, and we'll do a couple. We'll say A, we want to figure out 85 and 115. And then for B, maybe we want to do 85 and 130. So you can see how to set these up. All right, so basically what we want to do is we want to kind of draw our normal distribution and figure out what these values are. So we have some distribution. Once you get the hang of this, you don't really need to draw the curve. It's not too pertinent. But so we have our median. That's the first thing we identify, this thing that goes right through the peak. They tell us that in the problem. They tell us the mean is 100. And then they tell us the standard deviation is 15. So what we want to do is we want to count by multiples of 15 3 times on either side of that 100. So we would, above it, we would go 115, 130, and 145. So these are all IQ scores. And then on the left-hand side, we would do the same. We would have 85, 70, and 55. And the first question says between 85 and 115. Well, 85 and 115 are just one standard deviation below 85 and one standard deviation above. So according to that empirical rule, it told us 68% of observations were between 85 and 115. So we know the answer to question A is just 68%. Now, B is a little bit different because we're going from 85 all the way up to 130. So we know this first part right here that we're measuring, this part has area 68%. So we know it's 68% plus whatever area this happens to be right here, which I'll kind of shade the other direction. So we need to figure out that area. Well, that's 2 standard deviations above, but only 1 standard deviation below. So if I can kind of convince you with a picture here, what's going on is if you had some picture where we did 2 above to 2 below, so we had this one and this one, 2 above to 2 below, from here to here, this is 95%. So from here to here is 95%. But as we said, from here to here, this was only 68%, that area. So if you did 95 minus 68, you would basically be getting these 2 sections. And I know my picture is not that great, but this distribution is perfectly symmetric. I've just kind of drawn it a little bit skewed. But if we did 95 minus 68, we would have the 2 shaded sections. So this would have area 95 minus 68, which would equal 27%. Now that's 2 of the sections. So this one little section that we're trying to figure out up here, this would have half that area, which would be 13.5%. So basically, the answer to B is this 68% plus 13.5%, which comes out to 81.5%. So that's what I mean with these symmetry arguments. If you know what you have on either side, then you can divide by 2 and get each one of these sections. So we can actually figure out all different parts of the normal distribution if we wanted to. doing that thing. So maybe that's worth looking at. So let's try to figure that out. So I know it's the 68, 95, 99.7 rule, but really we kind of have 4 different shapes going on in here, because we have 1 above, 2 above, 3 above, and then kind of what's left over. So we've got a piece that looks like this, the tallest piece, then 1 right here, and then 1 right here, and then the tail that goes all the way on forever and ever, but amounts to very little area. So the first section, we could use the symmetry argument, right? You have the same sections on the either side that are also symmetric, but we just want to figure out what each piece is, and then we could figure out any possible percentage, really. So the first section adds up to 68%. So 68% divided by 2 would tell me that if I just looked at this section right here, this would have area 34%. We just figured out how much this one would be on the previous problem, right? It would be 95 minus 68 divided by 2, which would be 13.5%. And then you would do the same trick if you were trying to figure out this one. So if we're trying to figure out this area, what would be happening? Well, we'd have our one normal distribution that has area 1, 2, 3, 1, 2, 3 from here to here. This has area 99.7%. And then if you subtracted the one that went from the middle to 2 above and 2 below, between these two, we only have 95%. So if you subtract those two, you get 4.7%, right? And what that would be leaving you with is, you know, the 2 pieces from the middle, 1, 2, 3, so from here to here, and 1, 2, 3 from here to here. So if you look at both of those areas added together, they're 4.7%, so if you divide by 2, you would get this area, which is 2.35%. And then this last area, if you look at 3 above to 3 below is 99.7, so if you look at both of the little tails on the end, they add up to 0.3%, so this last one right here adds up to 0.15%. So that's not the best picture in the world, but kind of you get the idea. All right, so maybe we'll look at one more problem where we can kind of figure that out. So let's go ahead and do one more kind of silly example that I've worked out before. So, and again, there's lots of different possibilities. I just was coming up with something kind of silly. So the weights of, I can't remember where this came from, but it's the weights of adorable fluffy kitties or kittens are normally distributed with a mean of 3.6 pounds and a standard deviation of 0.4 pounds. So find the percentage weighing between, so A, 2.8 and 4.8 pounds, B, less than 2.4 pounds, and C, let's say more than 4 pounds. So now knowing all those different sections will help us answer this question. So again, we want to draw a normal distribution, and really we just care about the marks. So we want to figure out 3 standard deviations above the mean, and 3 standard deviations below, and the picture looks like this. I keep drawing the picture even though to answer the question we just need to know what those values are. So the middle value we said was 3.6, and we're counting by 0.4, so 4 more is 4, 4.4, and 4.8. Below we would have 3.2, 2.8, and 2.4. So for the first question, we're going from 2.8, so this is the middle of our distribution. 2.8 is 2 below. 4.8 is 3 above, so we're 2 below to 3 above. So 2.8 to 4.4, this part would be 95%. So this would be 95% 2 below to 2 above, plus one more little section, the section from 2 standard deviations to 3 standard deviations. So if we look back here, 2 standard deviations to 3 standard deviations is this 2.35%. So that's what we have to add. So 97 plus 2.35, that adds up to 97.35%. Okay, and then B and C are actually about the tails of the distribution. For B, we're looking at all the parts less, so maybe I'll use some different colors to shade. So I don't know, we can use yellow for B, yellow, we're looking at shading this area, 2.4 and below. So that's symmetric to the tail on the right hand side above here, which we had as 0.15%. So we know that that is going to be the answer for question B, 0.15%. So this is just equal to 0.15%. And then more than 4 pounds is a little bit different. So more than 4 pounds, I don't know what color this is. More than 4 pounds, so this color. We're going from here above. So more than 4.4 is including both the 2.35 and the 0.15. So we add those two together. So we get that would add up to 2. More than 4 pounds, not more than 4.4 pounds. So sorry, I need to adjust that a little bit. So actually we're starting here and going on. So we have all of this. So we're including all of that. So if we go back up, it's going to be the 13.5 plus the 2.35 plus the 0.15. So we have to add all three of those together. So for part C, we have 13.5 plus, actually let me go back to the other color so it's easier to read. 13.5 plus 2.35 plus 0.15. So our answer there would be 16%. All right. So that is it for the normal distribution. That's all we'll look at as a couple of examples with a normal curve, and hopefully in the empirical rule. So hopefully that will help you out if you take another class in statistics in the future. But for this class, that's all we're looking at in statistics, these two sections. Okay, this is Dr. Lennon signing off. Please let me know if you have any homework questions, and I will be sure to reply to you.